Because
Yeah.
it's open source.
So like a Red Hat version of.
No, it's not even like hacking. It's just like 100% allowed because it's open source.
Okay.
And some of those are less ethical than others. There's a controversy about that.
All right, well, we're gonna get started. So I'm like super excited about seeing your presentation. So we're gonna have about 5 minutes. You can go, between like 5 and 6 minutes, and then we'll have a few minutes for questions and comments, and then we'll move in to the next person. So I think like for the purpose, I guess we don't have it to do it in order. So is there anyone that would like to go first? Okay. Okay, that's easy. So I just go to my drive, to my Gmail, right, and see.
Yeah, I shared it with you.
Okay, this one, HB.
No, it's like
That's me.
Oh, okay. Perfect. Just open, or do you want me to download?
I think you should just be able to open it, and it'll just open it in slides. Yeah, and you can just present it from there.
Okay. So,
All right, it's recording and everything?
yes.
All right, perfect. Carl, do you know how to do this so it shows the speaker notes?
Presenter view, I think? Question mark?
What's that?
Oh, but it's got to.
Oh, yeah, it's not what we want.
No, that's not exactly what you want.
With that
because
one,
it's,
oh, you won't
it's
have.
mirroring the screen right now, right? You need
This
to
is
do an
fine.
extending the screen.
Do you-
If that's, I'm fine
You
with
need
that.
your
I don't
need
notes.
this speaker
I don't
notes?
need it.
Okay.
Okay. Yeah, this is good. Okay. Oh.
Back,
Oh, wait.
back.
Oh.
Just any click and it
Got
ends
it.
the world.
It goes forward. Okay.
Hello, everyone. My name is Carl,
And I'm Trey.
and we are both going to present on the extreme relative pose estimation via scene completion, aka video number 4. So, Trey, you want to take it away?
Yeah, mouthful of a title. So basically, this video posed a problem, and that's when we're scanning 3D scenes, right? You don't always have ideal environment and ideal conditions. And so in order to get a really good, clean, 3D model from, let's say, this room, you'd have to take millions and millions of photos from millions and millions of different angles in order to get all the different geometries in the room and all that kind of stuff. And so right now, this method is proposing a new way to estimate what is in between angles, what's in between the scenes. So take 2 photos and be able to figure out what would the photos in between look like, and be able to get the 3D model or the 3D pose scene from that. But there's some big problems that the current versions have, and that's they're inefficient. They can be inaccurate when it comes to, is this one object, is it 2 objects? Current methods have no idea what the object is. They don't know if it's a chair or a table or a wall or floor or a plant or anything like that. And then also they have no scale of is this all the same scene? What are the differences? And so it's hard to tell the differences between the 2 different angles. And so this paper proposes a few different solutions in order to make a good comprehensive solution to this problem.
Awesome. So the 3 different solutions that we'll talk about. First, a quick note before we talk about the extra solutions that go into. When they were training these models, they were actually taking full scenes where there was the entire scan of the scene via almost like a panoramic type shot. So they'd have the full panoramic shot, and they train it by taking out 2 different images from that panoramic shot and try and recreate that panoramic shot. So that's what the training behind it. So there's 3 kind of novel approaches that they choose to discuss in the video. The first thing that they felt was really critical and important had to do with something we don't actually have an image up there from, but it's this idea of based upon or inspired by how we as humans understand objects. We have lovely Trey here. Trey's going to T-pose for us. And if I were to see Trey from this direction and then turn him around and see him from this direction, both of those different views that I see are independent of each other. They don't have much overlapping data. And yet I can still in my mind determine what the intermediate states are. And it's because I know Trey is a singular object. Not to objectify you too much, buddy, but he is one object, one entity. And so they said, well, what if we incorporate this also within our machine learning program? within the neural net, let's make sure it knows that these two images, while they appear different, are actually coming from the exact same entity, the same room or the same landscape. Now, the second thing that they chose within their solution was that they chose to have 4 different types of mappings in order to show these RGB scenes. So they first start with the color mapping of the image, which is just the pure color, but then they also do a depth mapping of the scene, the normal map of the scene, and finally semantic descriptor. Semantic descriptor is kind of like object detection, talking about, this is where maybe a cabinet in the room is, or a light in the room is. And they use each one of these 4 different things in order to train the model. The final kind of novel approach that they chose to use in this paper was the idea that if an image was used in the input, then that must have been a ground truth to what the scene was. And thus, if that's a ground truth, it must appear in the final output. If it doesn't appear in the final output, then that means that portion of the image is more wrong than it could have been. And so they chose, if we kind of look at this general layout here, this idea of recursively using the 2 scans in order to keep on updating the scene and use their own 2 separate kind of neural networks in order to allow it to get these 2 parts of the scene to be 100% correct. Because if we have the image already, then that must be a ground truth. That's the 3 main novel approaches to what we have. You have any other things you want to talk about?
Just that watching this video, this kind of reminded me of a GAN model where you have one network that kind of generates images and the other that checks it. In this situation, they have both that are kind of generating the scenes and then cross-examining each other and then going back and redoing that if it's incorrect.
Awesome.
That's
so,
it, yeah.
Yep, that's our general presentation. We'd love if you guys have any question for us.
And
Final sources.
all images were sourced from the video and the paper.
Is there a way that you can zoom in on the second slide? Like, I want to see kind of like both of those separate.
Oh, yeah, let me...
Duplicate the slide, delete one image, expand.
do some live editing here. Hold up.
And it's live.
Yeah, from New York.
Oh no. Command copy, not control copy. There we go.
Okay.
Whoa. Unfortunately, I think this is the one that I had to screen grab from the video because it wasn't in the paper. So it's a little...
Also, you found the paper as well?
Yeah,
Yeah,
we found
so-
the paper was published in 2018. I think under Cornell University is what the GitHub linked back to. I also found the GitHub as well.
So we used all of our images either, we had one screen grab from the video and the rest are taken from the paper themselves.
Okay, there you go. Is that the one? Is that the image you wanted, or do you want the other
Yeah,
one?
that one and the other.
And the other one. Okay,
Okay.
hold up.
So while you're
Yeah, while he's
that,
doing that, any other-
I did have a question
Yep.
from the beginning. So they only need 2 source images?
Yeah, so that's what they,
Two.
yep,
And then like they are different rotations of the
Yeah.
image.
So if I were to, for example, take my phone and take a panoramic shot of this room, okay? That's going to be like the output I want to generate. And then it's going to take the 2 inputs, or let's say if I took one picture, smile guys, one picture here, and then those 2 images would try and recreate essentially that panoramic scene.
I misspoke earlier when I said model. I meant like a skybox of the room, essentially.
Yep.
Yeah.
And they actually used the skyboxes in the original training. They just chalked off the upwards view and the downwards view from the skybox, so it was only a panoramic scene.
You think it's you said it was like your phone, but I don't think your phone has an RGB scanner, which includes like the depth data. So do you think it's kind of like cheating if computer vision is using that depth data? That's just more of a philosophical question.
Define cheating if you're the one making the rules, right?
Well, I'm saying if you're trying to replicate like human vision,
Oh yeah.
I don't think that we're not using echolocation or something to like sense the depth of each thing.
We have two eyes, so we are sensing the depth via that, what we focus on, right? So would that not be considered a depth sensor?
Yeah,
I
I
think it's the same.
No? Okay.
That's fine.
Yeah,
Yeah, I
I,
don't
I, I think there is some differences that it's not perfect about, right? And I surely can see the idea of going into a stereoscopic version of this if you wanted to more closely relate to human perception. The video, I would say, probably didn't, or was a little bit less concerned with perfectly mimicking human vision and trying to get a little, just solving the problem in general.
There's a lot of cheating in my video.
Yeah.
Okay, so again, to the two images. So it needs the panoramic plus two input images, or from the two input images they can create the scene. Just like, okay, the second one.
Yeah, the second one. So the reason they were inputting they used panoramic images only as source material to test the network. So it's kind of like they had the answer key and they took like the questions and they gave it the question and then they just checked it off using the answer key that was the panoramic of a room.
And sorry, like if you don't know the answer, like that's totally fine because like I know it's pretty complex stuff.
Yeah.
But, like you talked a little bit about semantic classification.
Yeah.
So basically what it does is like it knows that this object is that object.
Yeah.
It corresponds.
I don't know it much better than the brief description I gave from the discussion.
That's what I assumed it was, is that they went in and labeled this is a chair, this is a ceiling, this is a floor, that kind of thing.
Wow.
I've heard a very, very basic overview with something like that. I don't know much more into semantic analyzation other than that.
Any other questions, anybody? Okay, so yeah, we can, thank you so much, that was awesome. Can move on to the next one. Okay, so anybody wants to go next? Okay, just play the video? Yeah. Okay. I like that. There's these, actually when you go to IEEE, there's this thing called fast track something where you have to do your presentation of your paper in 1 minute.
Ooh,
Yeah,
that's
it's pretty
exciting.
wild. But you did great. Like it was really good, and it was very engaging as well. So.
Actually, I couldn't make the slides for 3 actually. So my slides are like around 11. But also there is some extra slides if you are more interested. But my presentation time limit was 15 minutes and something seconds.
Oh, okay. We should. Well, that's fine. Like we should watch it. No, it's 5 minutes. Your presentation is 5 minutes. It's perfect.
Oh, it's recorded.
Let's see. Okay, hold on. Let's test audio. Okay, one more thing over here. Oh. Hold on. Just need to bump up the volume.
But for her freshman intro database class. Yeah.
Okay, hope now it's not.
When I went to the
Too loud.
grad mixer, I was like, I'm in one of your classes. She was like,
Hello
"Oh,
everyone, I'm
the
Nusha
intro."
Firdausi. Today I will talk about the paper screen understanding for embodied tasks. So let's first look on today's computer vision. So we know we have the data, then we apply some training algorithm on our data set, and finally we perform our task. So let's see an example. In this example, I took some shot of a video. In this video, a baby is walking on the park. He was falling some time, and finally he was able to manage himself to walk way to the other side of the park. So this kind of video streaming, we have some problem, we don't have any supervision. We don't have any fixed data set. Also, there are lots of data set which is not relevant with our task. So when we applied some machine learning algorithm on video data set, there is some problem also. So there is no fixed training and test boundary. Model need to learn about the dynamic data, and model also need to learn about the time constraint, and there is also the budget constraint. So it is really difficult for model to develop the task or perform the task. So if the task is static, like image classification, it is really easy to handle for the model. But what if the task is interactive? For example, video streaming. So this kind of task is really difficult to manage. This kind of task actually called embedded task. So this paper will talk about how to handle embedded tasks using AI. Here, Luca and Matt developed a task, and this task example name is room rearrangement. Room rearrangement tasks have two kind of phases. So first one is walkthrough and unshuffle. So in the walkthrough phases, agent will moving around the scene and observe the object where it is located. And in the unshuffle phase, agent first will be removed from the scene. Then the user will do some changes on the object. And in the end, agent will come to the scene again and undo the changes. So for this simulation, authors use AI to Thor simulation, where simulator of indoor scene. Agent can also perform navigation, interact with the object, like turn on the light or turn off the light. Agent can also touch the object and move the object. So their proposed model have two very important things, that is input and the output. So in the input, they have egocentric observation of agent pose, and they specify two phases, walkthrough or unshuffle. And the output is a sequence of action among four possible navigation and interaction. So this is the train test and zero shot cases. So I will only give the focus on zero shot cases where agent don't know what is going on in the scene, and user can also manipulate the scene. Here is the performance plot result. We can see that phase one, performance rate is much more higher than the phase 2's performance rate. And this is the success rate among the of the agent. Here the pickup success rate, we can see that pickup success rate is higher than episode success rate. This is because agent had a very hard time to reach the object to the particular destination. So because of that, episodic success rate is lower than the pickup success rate. And here is the result plot of novel scene and the object, where you can see that pickup success rate is as usual higher than episodic success rate with or without disturbance. So in the end, this paper actually talked about said their training model is faster than the other training model, and they have a better evolution generation of the models. They conduct reproducible experiments, and their simulation performs safe training and evaluation. So thank you for today's presentation. If you have any question, you can ask me. Thank you.
Okay, thank you, Bushra. And are there any questions about this? Clarifications? Anyone? So if I understand correctly, this was this is used for training robots or okay.
So in the last image, slide number probably actually.
Do you want me to open the slides?
Yeah, you can open the slide. Uh, 60.
Oops, sorry, got bright space is it's got stuck. Sorry, I don't know why it's doing that. Okay. What? Okay. It's like is
Yeah, just full screen.
Oh no, it's following his mouse.
You just press that.
okay.
Oh,
Okay, good.
Slide. So there is a robot, actually agent image, end of the presentation. Yeah. Before the slide, this one. So this robot had some special option, like they had waist and joints. So user can easily move the waist and joint. Also, each arm has some flexibility, so you can move around in any object, and you can pick the object, and after some time or after agent think this object position is not correct, it will move its hands and place it in the correct position. So this is the model basically they were using in the simulation.
Oh,
So
cool.
one of the goal of this paper, so why they should use this kind of simulation. So first they did some experiment on the real life, but that time it turned out very bad because when they working with some real robot, it was too much costly, it was time consuming, and after some time, like after 5 or 3 moves, that robot couldn't manage the task. So that's why their main goal was, let's do some simulation, use the same model as our agent, and we will use machine learning algorithm to train our agent, and this we will look on the result and see how the training process worked out.
Wow. And then which kind of tasks were given to the agent?
So in the example rearrangement, slide number
Slide this one?
6.
This one?
Yeah, this one. So in this task, basically they move some object from the scene. Like they have some toaster maybe on the cabinet of the kitchen, and also they have coffee machine on the kitchen cabinet or the kitchen sink. Actually, what is say the pink line, and the green line. So agent task first move that coffee machine and the toaster to the correct position. The arrow there is showing. So as their agent was successfully able to move that task. But they have some also other problem it arises, and when I already showed it on the result part. So agent can easily pick up the object, but they feel difficulties when they have to reach the particular destination. Sometimes they just reach some clash with other object. Sometimes they couldn't able to place it to the correct position, but picking on the object they was very much successful. So they are actually still working on that project, and hopefully in future they will come up with good results.
So they just feed videos of, for example, me making coffee every morning, and then, like you just give how many videos? Just one video or many?
No. In this simulation, they use AI to thought simulator. So that simulator had 84 scenes, but user can manipulate their scene, or they can also create their own scene. So using that scene, user can train their agent. So we can say like there is kind of customization tool or simulator they are using for training purpose.
Wow, it's fascinating.
Yeah, that's amazing actually.
Yeah.
And so in order to speed up the training time, they just run a bunch of instances of the generations and like train it really,
Yeah,
really
yeah,
fast. Okay,
yeah.
got
They're
it.
like multi-threading it.
Yeah, yeah,
Yeah.
yeah, yeah.
Yeah, it's really cool. I like that they did the coffee thing, because I mean, like, you need a robot for that to make it to make it right. It needs to be done by a smart agent.
Yeah.
Okay, that was very fascinating. Thank you. Okay, anybody wants to go next? Okay, Manuel. Do you have it in? Do you upload it here?
Yeah, I mean,
Okay.
because I thought that it was at 6 p.m. as usually, but yeah.
Yeah, no, it was. Sorry, it
Okay.
was my bad. Like, it wasn't at 6 in the morning.
Yeah, it was. Well, I mean, I have one class with Travis, with Professor First, that we have the deadline at 8 a.m.
Cool.
Oh.
So 12 a.m. the night before, right?
Well, yeah. Or you can wake up at 6.
Yeah.
Or you don't wake up, you just keep going till 6 a.m. in the morning.
Well, I mean, last
Which is
Friday,
the
Friday I wake up at 6, and I did it at 6.
dangerous.
I treat any deadline that's before 12 p.m. as at midnight.
I'm gonna remove one.
I just can't trust myself to wake up early and finish it. I can't.
I'm gonna remove this
I don't even
one,
have to
I think.
add
This one? Remove it? Just
No,
delete
this one. Yeah, I mean, yeah, only with.
You sure? I mean, you can leave it, and I
Okay.
mean, I don't know.
Yeah, well.
Whichever, whatever you
whatever,
want.
yeah,
Yes.
I don't mind. So, good night. My name is Manuel Contero, and I'm gonna present you learning the object in the 3D world. I'm going to simplify so much the video because it was so complicated. There were like so much terminology that I didn't understand. Well, I didn't understand. It was not related because it's not my field about the 3D modeling in that space. I mean, I'm more in 3D CAD. So anyway, what I tried to perceive on this video was these three methodologies. Well, this methodology that follows the author in the video, that is data, representation, learning, and correspondence. And I was trying to relate these three things to our readings of our last weeks, because in data, what the video was telling us was that you can grab an object, like an apple, for example, or this water bottle, for example, and what he was doing is take photograms all around the object, you know, and in that way you can know how exactly is that object. But then you go to the next step, that is representation and learning. So how do you know that an apple is an apple or a water bottle is a water bottle? So you get different water bottles or apples, and you do exactly the same thing. And then he applied like different technologies to get a better approach of the representation of that bottle. So that's the way that representation and learning step is. And then the correspondence was trying to generate the object with all of these images. Like, I don't know if you have seen, like, I think last year or whatever, I think with machine learning you can generate objects. You put like different stuff and you generate a new object. So that's what he was trying to do with like taking an approach of different apples or different 3D objects. So here, well, this is a random pic that I put, but anyway, here is something that he does to get an approach of how the object looks, like the apple, for example, of that plant. But here, that's what I was telling you about the training step, that is getting a bunch of different photos of different, that thing, I don't know how it's called in English, and either in Spanish, but anyway. Okay.
Hydrate, sorry.
Okay. And well, then try to reconstruct, and after in the output, it gets the best reproduction of the 3D model of the object. And that's it.
Wow, it's amazing.
Thank you. I mean, it was super complicated. If you see the video, the full video, I mean, there were so much stuff that I was like, what? So it's complicated to resume.
I've got a quick question. Yeah. So those 10 fire hydrants, are they the same one, or are they different ones from different places even?
Yeah, these ones. Or what?
Those 10 object videos.
Yeah, that in the training. You
No,
mean?
I mean, are they the same ones or are they different ones?
Yeah, so the first step you get like the one object, like this water bottle. But then in the second step, you're gonna get a bunch of water bottles to train the algorithm to get later, like in the end, in the output, like the best representation possible of the object. And also like in the middle that I didn't put in the slides because it was quite tricky, was the procedures that they use to like get the best contrast to see the shape of the object, blah blah blah, and after how to develop the best 3D model possible with procedural modeling and other stuff that I was not that much related, so I just skip it a bit.
Yeah, but I appreciate that you explain it in a very approachable way, like understandable.
Yeah, for me, it was the example was an apple. Like when you're a kid, I mean in the review that I did you'll see. What I try to do is like, for example, when you're a kid, you don't know what is an apple, and that's the same thing for in the in artificial intelligence. Doesn't know at the beginning what is an apple, So what you try to do with the camera is to learn, like as a kid, you touch it, you see it around the apple, but then you don't know it's an apple. You have to see other apples. They have different shapes, different colors, and in the end, you know that an apple is an apple. So you can imagine in your mind, with the closed eyes, how it's an apple. So it's like the same, I think, in the end.
I was just thinking about like the video that Trey sent me about plateau.
Yeah, I was thinking about that too. Yeah.
About like the world of the ideas and how these you gotta like feed the machine like all like the database of the idea of what a hydrant is, and then from that it extracts the characteristics. I mean, it's something like a lot from philosophy, but this is like a real thing, and like to me it's amazing. Like having like a possibly like a object. I don't know what kind of that, but like if it's like a mesh but it has like materials too. Like he embeds the materials within the 3D object.
Yeah, what I see is that like in this topic in this video, I don't know, but what is artificial perception? Maybe in the future, we are seeing a lot of things, but I think that artificial perception could be a quite interesting topic in the future, and also like with creativity, with design, and all of this, can place a huge step, like taking out of the way the designers, just with a computer. Yeah, you can just put a bunch of data there and take an output. So it's super interesting.
Yeah. I've seen like some apps that are AI art. They make really cool compositions. Like it's almost like it takes all the history of art and knows what's a successful color palette, what's a successful composition, and then it turns out some really cool work. And I was thinking about you, Manuel, and also Christian and Modena, who are in manufacture, because a lot of the applications of these algorithms are, for supply, like for all robots that build things and quality control.
Yeah, no, totally agree. And also, like, I was thinking, I mean, one of the classes that I love in an undergrad was emotional design, where it's also related to visual intelligence and perception and all of this. You can get like different approaches of a product, the characteristics, the features, and I see that can merge the two things in the creation of beautiful, stunning products. The two of them. So.
guys don't mind, I want, because my topic is somewhat related to this.
I'm gonna open your presentation.
Okay.
It's like eerily similar to my thing.
I'm pretty sure there was a guy. I think so. I know that. He did it right with the
You want me to do slideshow?
Yes, yes, please.
Yeah. Okay. Thank you.
So hi guys, today I'm going to introduce this video lecture about neural scene representation and rendering. Okay, so let me start off by letting you guys imagine participating in a football game from your favorite player's point of view. For example, Super Bowl Sunday, and you you see whatever your favorite players sees. You feel the game dynamic from his own point of view. You see how he throws the ball and everything. How cool is that? And how about also walking around the sideline with the coach, maybe? Hear about their conversation? So if you don't think that's cool enough, think about playing a concert as the guitarist with your favorite band virtually, and maybe attending Olympic Games as if you were the actual athlete. Okay, so these are all the things that we could have never seen before. Maybe in the future we can. So all thanks to this technology called neural scene representation and rendering. So what it is about, I'm gonna show you guys a short video clip.
Our next speaker.
It's not working, so I had a timestamp on there. I don't know why it's not. Okay.
Shape of these objects. And so you can see that at that location. So using this idea and this generalization idea in particular is powerful, because now once trained on a specific class of objects, we can now take individual images of objects, so just a single 2D image, and predict the full 3D shape of these objects. And so you can see that.
So our next speaker is.
Let me stop there real quick. Let me. I actually hit the space button. Okay, so the top one is like the author's work. So obviously you can see it's much substantially clearer image than the previous work, and so this is like after 50 observations training, and the input is only one image. So it's like generating the 3D model of that object from one image after training. Okay, so let me show you guys another.
And this generalization idea in particular is powerful.
Yeah.
You know, move from modeling these ShapeNet objects to modeling photo.
So this is also generated from one image. So it's kind of creating the dynamic view from different viewpoints, but it's like all coming from one image. And we go next. So that short video clip is talking about generating 3D object from one image to the image. But this one, of course, it doesn't go with the, okay, times. So what this one is doing here is that there are 3 images. Those are the observations. And from the observations, the algorithm understands the spatial relationships between those several objects and automatically renders like the 3D model of the whole scene. And you can choose wherever your point of view wants to be. this is only from one image even. Okay. And is this another one? No, this is the one. Okay. So this is from their work. This is just illustrating that from one picture they can they can form a virtual point of view. It's like actually it's like a virtual camera, and analyze all the pictures, all the light rays that's coming into the camera, like renders the kind of fake scene from just one image. And yeah, so let me say that in the future the camera can be anywhere. So this is different from wearing a 360-degree camera, because that for that thing you can your point of view is fixed, either on your head or like in front of your chest. And also think about in this concert, there are maybe millions of subscribers sitting in their couch and using their VR headset, and each of them have their own chosen point of view. They have like each of them may have like their own favorite player of the field. So this requires large amount of real-time rendering and super fast, computation speed. But maybe in the future, when we have quantum computer or something, this all come true, and we can, just experience, literally be anyone, and just in the couch. Yeah, that's all for me. Is that the last one? Oh yeah. Thank you. Yes.
Can
Yeah.
you look
Oh
at
yeah.
your works cited page, your reference page for a second?
My reference
Yeah.
page. I'm sorry, I don't have a reference page. Yeah. These are all from the video.
Okay.
Yeah, from the.
The reason I asked was you brought up Nerf in there, and
Yeah.
so from my understanding, Nerf is not a one image thing. It's
So all
not
this was
100
before
images.
Nerf?
Yeah, that's Nerf. So the rotation stuff, I think that's 100 images that end up creating one scene.
100 images from different angle,
Yeah.
or.
Because that's what Nerf
Okay.
is, right?
Okay. Maybe I'm wrong.
And I'm not sure. That's why I'm interested in looking. That's why I was interested
Okay,
in the references,
yeah.
because I wasn't sure.
In the later part of the video, they have like generated.
There to get photorealistic, high quality results, but we certainly made a big step over some of the recent work that's.
Yeah. So.
Okay.
Yeah.
Sorry, I just asked because if they made Nerf work with one image, that's insanely huge.
Okay. Okay.
So, okay.
Okay.
What's NERF stand for?
Nerf is a neural rendering field.
Okay. So the E is just.
Yeah.
So I had a question about, like from that single image, does it like go to like a database of 3D models? Or like how it can, for example, recreate the car
Yeah.
from just the image in 3D? Like it must have like some sort of connection to a database.
Yeah, I think that's through the training. So in the training, so the algorithm gets like multiple images from maybe different cars, and so that he knows like what to expect. On the back side of the car, there are also going to be two wheels, or kind of stuff. Yeah.
Because I mean, just like speculating a little bit with this world that we live in, where like all products are virtually designed. Like it could be like this thing where everything is designed, goes to a database before it even goes
Exactly.
into the market. It's already a digital product.
Yeah.
So like it could be very easily implemented into like a whole
Yeah.
world, type
Yeah.
of vision. Because like it could be like regulated that like this chair
Yeah. Maybe.
model.
Yeah. In the future, maybe all the objects in reality are replications of NFTs, right?
Yeah.
Yeah. Yeah.
For sure.
Yeah.
Well, that's very cool. Yeah, we can talk about NFTs too.
Thank you.
I mean, it's interesting too because I mean,
Yeah.
there is kind of like a fear that everything's gonna be tokenized. Okay, anybody who wants to call? Oh, okay, Lucas. Is it on Brightspace?
Okay.
So then it's still
Maybe I should download it better.
Yeah, that's how
Thanks. All right, thank you, Lucas.
So I didn't look at any of the other videos. I only looked at mine, and I didn't even realize that they were so closely related. I knew they were all part of the same kind of presentation, but I didn't realize that they were all basically on the same topic, just different methods and whatnot. So mine was learning to detect geometric structures from images for 3D parsing. And just like some of the ones that we've seen already, you know, the concepts are somewhat similar, but the way that they went about and what the end result was is slightly different. So one of the things that they explored in the video was the kind of traditional 3D reconstruction pipeline, which featured a lot of feature extraction and matching from images, multi-view geometry, so kind of like what we just looked at, where you know you have images from different angles, and then that's how you can approximate geometry, and also point clouds. And point clouds, if you're familiar, you know it's kind of like you can use LiDAR and those sorts of things in order to generate geometry, but a lot of times that result is very heavy because you know you're calculating vertices for almost every ray that is cast. So these didn't really work for the goal that they were trying to accomplish, which was to generate 3D geometry from a single image and do it accurately and be able to approximate what the planes are and create almost like a wireframe of the scene. So the new method, or the method that they kind of derived from their research, is mainly data-driven. So it was slightly different from the other methods that I just showed you because, like, for instance, the point cloud was just like a single method of gathering the data. But what they found is that by using a combination of a lot of different methods, essentially, they were able to more accurately get the 3D geometry from the scene. And so the first step that they do is kind of a data representation. They did a training model to learn how to reconstruct 3D wireframes from single images. And essentially what that does is it finds lines and vanishing points. And even though the vanishing points weren't super accurate all the time, it was a very good starting point to figure out where geometry was located and how far it stretched in and out of the scene based on the depth. And then they went to, they call it end-to-end wireframe parsing. So basically they took those wireframes and they were able to generate the actual 3D structure. So it was able to determine the back edges of a table and do some mirroring on symmetrical objects and things like that. And then they used a neural network that was basically, it was focused on generating a more perfect version of the vanishing point in the scene. And with that vanishing point, you got a perfect perspective of the image that you were trying to essentially determine what the geometry was. And then the last step is the neural 3D reflection symmetry detector. Like I said, they basically were able to take objects and train the model by saying, you know, okay, this couch stretches into the foreground, and it can basically just split whatever those geometries were in half, and even if they're occluded, it could still determine what those back edges were going to look like and things like that. So the application that they developed is called Holy City. I think it's Holly City. I can't remember how you pronounced it. But essentially what it does is it looks at these images and it's able to do a plane detection and a normal estimation of the different geometry in the scene. And so you can see, very similar to, I forget which one it was we were looking at, where they kind of generated normals for the scene that they were looking at. They also used panoramic images to train it. And so you can see all the way from the left, you've got the RGB images and then the ground truth, and then the trained ones, you can see where the colors are overlaid over the image. It was able to accurately determine what planes were, even with the panoramic image, which is kind of warped, it was still able to generate pretty accurate geometry. You can see all the way on the right that it was able to determine where the different planes and what those normals were in the scene, based on a combination of things like there's geometry and vanishing points, and then it uses that wireframe to then populate those faces, essentially. I think that's the last slide. Yeah. But I was just going to add that you know, the thing that I got from the video, it was pretty complicated and it was a little difficult to follow at times, but the thing that I really got from it was the fact that they claim that even though, you know, there are a lot of random structures and random things in nature, for the most part, especially human structures, it's a little bit easier for a computer to determine certain things because parallel lines create geometry essentially in space. So by adding a lot of those different methods and some of those neural networks, it was able to, you know, more accurately determine where some of those geometry were in space, because, I mean, patterns, and the more data you feed into the system, the more it adds to it. So that's it. Any questions?
Did they say if Holly City was a real city or a virtual generated city?
No, so Holly City is the application that they created. That was the name of the.
Okay. Were they using the input images of real cities or virtual? Okay.
Yeah, they were panoramic shots of actual cities.
So I'm assuming like the name of the application with the word city is because they're like, what do they want to use it for? Like, it's something related with cities, but what is like their
Right. So I think the reason they called that one Holly City is because most of the data that they trained it on were images of city structures, so buildings and things like that. And I don't know specifically why they went with that. It could have been that was just the data set that they had. But over the course of the whole presentation, I mean, they talked about interior images. They did a lot of work with like not landscapes, but like tables and things in rooms and room scenes and stuff like that. But when they trained their model for that presentation, it was all images related to city structures and buildings and bridges and things like that. So I think that's why they went with that, but he didn't explain that in the video.
I would assume because it's like big geometric square things that you have a lot of perspective for. So like, especially with the vanishing point thing,
right?
In this room, I can probably pick out maybe one vanishing point.
Right.
But if you're in a big city like that with a lot of sharp angles,
right,
make it a lot easier.
That's true.
And specifically a city with a lot of human-made structures, as opposed to in nature or even a rural area. You know, you've got one human structure, a barn and a house. Then beyond that, it's trees and fields and other things.
Yeah, and I mean, they really stress the importance of being able to determine the vanishing point in order to get the neural network to assume a lot of the geometry, which I found really interesting because, I mean, all the physiological things that we've learned about like our eyes and our brains, it almost seems like training neural networks and machine learning and computer vision is just trying to get them to learn what we learned as babies, you know? So
it's like neural networks are based on the brain.
Right.
Yeah, perspective is not very easy to perceive.
Yeah.
Right.
You kind of have to, I don't know, like if any of you have like different drawing classes, like freehand drawing, then you kind of like learn to see it, but otherwise,
right,
it's almost like it doesn't exist.
And I feel like most of the sketching classes that I've had and drawing and stuff, when you're learning how to represent perspective, you pretty much always start with the vanishing point which is why I think they were so focused on getting the vanishing points to be accurate in order to get that geometry represented. Any other question?
Okay, so question for you all. You want to take like a 5-minute break to bathroom or something? Yes, you need to break? Okay. So yeah, we'll be back in 5 minutes or 10 or 5. Okay. Just come back.
Don't go home.
I'll be here.
You have that moment about third away through the video where you're like, I'm glad I took that AI class because I kind of know what they're talking about now.
Yeah, pretty much. Pretty much. I didn't realize how much that was going to play out.
Yeah. Do you want me to tell you more about the new stuff?
Yeah,
Yeah, cool.
sure.
Awesome. And so,
It's really cool, but I've been dreaming about being able to watch games or the whole time. Didn't know about this technology.
I'm interested in it because I have this, and I talked about it in the reflection of my computer. But, and so I think, I mean, I want to be able to.
Okay. Thank you, Avinash.
Right, like, that's what I'm doing. You know?
So we're back. So now it's Avinash.
So hello. Wait, I'll just put up a timer because I have a lot of text to talk about. Yep. So the topic, the video I was working on was training home assistants to rearrange their habitat, and looking at all the other presentations. This was very similar to what you were talking about. Even Bushra's presentation was like very in line to that. So this project was basically initiated with Habitat 1.0, which was more like a research paper about simulator for navigation research problems, where 3D scans are loaded for robots to render egocentric observations and train for navigation problems. This was like gradually evolved into Habitat 2.0, which develops systems for mobile manipulator for fetch robots that can navigate and interact with objects, open drawers, and take objects from one point to the other. So they basically need a few things to reach their objectives, that are like 3D assets, simulator capabilities, and and tasks. These tasks are basically home assistant benchmark, which start with pick task using a fetch robot with onboard sensors like a head camera and an unmounted camera. And these tasks are assigned using simple programs like tidy house, prepare groceries, and set tables. And these tasks are basically allows the robot to like train for clustering and declustering the arrangement that is in front of it. Going forward, this is basically how it's trained. Like there is a set current state, and there is like a desired goal state, and based on this, the robot is basically allowed to like check and scan the surroundings. They use a lot of 3D scanning, but since direct 3D scanning baked the objects into the render, they hired like individual artists to create multiple objects that could be interacted with. Like all the objects in the replica CAD are basically individual objects that the robot can actually pick and place into different places. This is the success rate of the tidy house task, which is like broken down into sub tasks like pick place, and that entire collective becomes the tidy house task. And that is the success rate that has been improvised partially, if not fully, by the robot using this program. Some goals that they have been using in the navigation system are like geometric, which is like kind of it's geometric in a way that they have to determine the center of mass and the coordinate of the object. Then language, like you have to describe what task you have to perform. and by image, like a final image of the arrangement is given to the robot, and that in turn basically does the job for the task that is assigned. And there are some challenges that they are still working on. Is the challenge between perception and memory of the robot, navigation and planning, and manipulation and communication. The other thing that they assumed while making this program was the world is for the robot is basically composed of rigid bodies, and they are excluding fluids or any gaseous or any deformed bodies at the moment. And the robot is basically not supposed to have any pre-computed maps or no knowledge of 3D models. This kind of reminded me of the conversation we all had about blind people interacting with different objects. Like if you don't have any information, how do you interact with an object, and how do you have a sense of what the object actually can feel like? And another thing that they have like been working on is the GPU rendering of how the image is scanned. So as far as the rendering goes, they render 128 by 128 pixel images, and using one GPU core, they render up to 1,000 images per minute. And when they use the image at its full-fledged capacity, that is like around 6 to 8 GPUs, they create at least 8,000 images per second. And then that's how the robot interacts with the objects more accurately. That's the basic idea of what this video is about, and they are continuing to work on that to make it more efficient. Thank you.
So in this GIF, it kind of looks like the robot arms just snapping to the object. So I was wondering, is this like simulating like the physics of the room, or is it just focusing on like the task logic of going from point A to point B? Because it just kind of looks like with this, like it goes in, misses, and then it goes back out, and then it just like snaps to it, right?
I mean, this is more like a simulator,
Yeah,
but
okay.
at the same time, it's basically like you are supposed to perform this task, and that's what the robot is supposed to do. But in real world, it actually it does work in a very similar way, that it detects like where the object actually is, based on like sensing the coordinates, and then it picks it up.
Okay, so they were testing this in real world.
Yeah, so this is they first initially simulate it, and then they implement it in the real world.
Okay. I thought this was all similar to your presentation, where they were just like testing a bunch of virtual robots. Okay.
No, that was like the initial project. What they were like, Habitat 1.0 was pretty much a simulation.
Yeah.
Now it's more like a mobile simulator that actually can be implemented in the real world.
Okay, good.
So this robot only works in this particular apartment. Right, like it has very busy environment. But it's only for this environment.
So there are different environments that are scanned, and that is fed into the robots. So this is not the only setup they have, but based on the scans and the 3D objects that are there to interact with, the robot itself learns to interact and pick and like do these tasks.
But we couldn't like just put this robot in an environment it's never seen before to just do stuff.
Not at the moment, no.
You have a robot?
Oh yeah.
So good.
It's really interesting. Cables there.
That's my cable.
No, just not a cable. Yeah, beeping in my living room.
Yeah.
People take that.
You have one of the robotic lawnmowers. Automatically mow your lawn. Yeah, it's really fun.
This reminds me of Final Destination.
And the floors are all over the floor, so I can't use anything. I've looked into accidents that happened to a Roomba and that they were indoor dogs. You know that?
Oh, we had a dog that hated it.
Hopefully the cat aspect, right?
No.
Maybe something like fit on top of a Roomba that like picks and like removes it.
On top of all
This may be more of a GPU like thread efficiency question, but you said
Mhm.
it was 1,000 images a minute on one core,
Mhm.
and then 8,000 a second on 8 cores. How does that work? Does it scale
That's
exponentially?
what how it was explained. I
Okay.
didn't look into it much because like, anyways, it was going above me. So.
Okay.
Alrighty.
I missed that part with the free cash.
I mean, even I was confused about
Yeah.
that.
Yeah.
I was like, that's a bit much. Maybe
Yeah, it
you.
seems like a
maybe
lot.
you're using like 100 cores and then that's what the physics.
Well,
It could be
like there's
over.
ways to do it with like if you use like OpenMP or something like that. So,
And maybe having multiple cores work on the same image at the time is faster for some reason. So maybe it will feel like
yeah. You can also sometimes do weird things where like I don't know if it actually helps this, but like if one image is one area is close to another one, then you can like pre-assume
Yeah.
that like you can
Gracias.
have a pretty
No.
long start time and then learn from that as opposed to
Okay, hi everyone. So, as to manual, this is out of my scope, totally out of my scope. I'm like, okay, I'm going to explain this to you, especially because you know the terminology and I don't know almost anything, but I did my best and I also did a kind of research to understand this a little bit more. So this was of talking about the learning to move and moving to learn. The first struggle that I had it was about the concept or the definition of learning, but it's another thing that maybe it's a takeaway that I'm going to tell you at the end of the presentation. So the objective of this is to recreate of all these projects that they were talking about was to recreate the speculative predictive predict a process about what is possible or not to observe like directly. They were talking about like a bunch of information of previous work about mapping and how to do it, and they were talking about like the current work about learning via interaction, the reinforcement learning. This is really interesting. It's really really interesting because it's like conductism in psychology, and the problems that they were stating about this current work is that there are very large sample complexity. Training by simulation only, it's a little bit complicated. It's also really expensive, and sim to real transference it could complicate a little bit more this kind of training the robots. So the solution for them is to use egocentric videos of people walking around their environments. In other words, they were intending to use real estate videos and how to use them to train the robots, and after that to create and recreate all the maps and so on. So here they were having a couple of questions about like what is next to what, and after that where can you go from one point to another, and how to do it. And they created for here like three kind of different research. One of them is about the semantic visual navigation by watching YouTube videos. The second one was learning navigation subroutines from egocentric videos. And the third one, they created a new framework called SEAL, self-supervised embodied actual learning. So for the first one, they had a kind of challenges. So one of them is that they were more related to the videos. So the videos, they don't come with action labels. The goals and intents are not known, and also they depict trajectories may not be optimal. So they have these kind of different actions to how to do that, or to how to solve those kind of challenges. The first one for videos don't come with action labels, so they were looking for extract information via inverse model. For goals and intents are not known, they were using off-the-shelf object detectors to label frames with desired objects. And to depict trajectories may not be optimal, they used a Q-learning to learn optimal behavior. After that, they got these three at the right on the right. You can see like these three options, no options, solutions. So the model that they created with the extracting the information, the goal labeling, and also creating a Q-learning quadruple. So something that you can see here in these screenshots, like the results of this. This is like the most complex of the three researches that they had. So from this one, after the robot was trained using the YouTube videos, you can see here in this heat map where are located like all the objects inside of the video, like a kind of prediction that the robot is having. Like, okay, we are going to predict that something after the training, after the second iteration or something like that, we are going to predict that it's something like a chair or a sofa or something like that. So it's like they having that. And after that, they are creating another kind of map, and this map is like other heat map, but this is more like in general, and is how we are going to predict this in the whole space. And finally, they have like that they created like a kind of policies. These policies like high level and low level policies. These high level policies are like after training the robot, and after that the low policies are more related to the action of the robot. Okay, yeah. So the result here is to finding objects of interest with this method does not require previous training, and has high efficacy to predict what is happening in or when it should happen in the next space. So the next one is about learning navigation subroutines from egocentric videos. So the challenges are kind of similar to the previous one. Videos don't come with labels, action labels, and possible to do multiple different things, but intents are not known priorly. So from here, actually they were just using the learning that they got from the previous research, and they tried to do that like with just their own robot and their own space. They didn't get too much. They say like, okay, we got some just more questions, and those questions were like how to seek data that provides opportunities for such learning for the robot to learn, and how to improve our models based on this data, because they were using the shelf of detectors. That's why they say like, okay, we know what is going to happen kind of, but now we want to know how we're going to combine with the previous research that we made. So from here, okay, yeah, the research question related to moving to learn. And from here, so they created the SEAL, self-supervised embodied active learning. Here they wanted to answer two questions. So how to seek the data that they were the previous questions, and how they are going to improve the models based on this data. So here you are going to see the previous work that it's kind of like that you maybe all know. The 3D semantic mapping, how to do the 3D semantic mapping. But from here, something that they made is to involve that, or to join this with the game curiosity generation, where it's like how that we are going to create that the machine or the robot here is going to be curious about what's going to happen in the next, or speculate about what is going to happen next. And after that, they do like a second part, that is the perception by itself. That is how the robot, after gaining the curiosity and after going to do the action, they are going to label that specific thing or object that is going to be in that specific other place that they were like going. So it's like a 2 steps process. The first one is the action one, to gain the curiosity, and the second one is about the perception, and it's a huge model. So the results here is that they gain a little bit more they improve their efficacy and efficiency. Here they are saying about I don't remember exactly, because the AP something, I don't remember exactly what it is, but it's like the exploratory policy, it's working better for them. It improved in a little bit, but it was like 5%. That is, to me, it's a lot, but it was an improvement of 5% for in efficacy, and also about the exploration policy as well, but in a different place, it was of 3.7% of improvement. And that's it. So learning to move is related to using egocentric videos, to learn policies for navigation, and moving to learn is related to seal, the seal model that they created at the end. Thank you. Oh, oh, it is.
I was wondering about like the videos. Like, did they ask people to submit videos? Like, was there?
No, they just took the ones that were in YouTube. That's it.
Oh, just people.
Yeah, the real estaters. So that I took this one. I'm going to use this one to train my robot, and that's it.
And they want to understand how people move in space.
Yes, yes. Yeah, the idea to them is also because they saw that training a robot could be very expensive. So how to train that out in a very low cost, but very high effective.
What does egocentric mean in this context?
The person is the viewer.
Person?
Yeah, it's like the person here, that who is filming the recording.
I do have a question specifically because we're like in education.
Yeah.
Right? So can you like really like explain to us like what do they mean by semantic?
Yes, semantic in this case means like, semantic in education and everywhere is like related to the words, right? To put a word to something, and this word is going to represent that something, that object. In this case, it's the same. Like how the shape and however is going to be or whatever is going to take this name. So a chair is going to be called a chair because it has some specific functions, some specific shapes, or some specific ways to be in a being way. Okay, that's semantic in this case, to define or to give it a definition, object.
So in the case of like this research, like you said that there was prior research that had already done that part, when they had a kind of like a database of descriptions.
Yeah, it's about this one in a specific, like it's more about this one. So this is going to be a chair, and this is a chair, and we are going to call it as a chair. But they have a different kind of database, a big database about chairs, different kind of chairs. So the robot at the end is going to define like, it's going to identify, this is a chair. So conceptual chairs are no for them.
Or like something that like it's outside of the design.
Yeah, outliers of chairs. I'm not like, okay, no, no, of this if they are not in the database. So
Any other questions? Anybody? Thank you. You have it on right space? Looks like a robot,
Well, if you give it to a robot, then what would they see? Would they see themselves?
Yeah. I've seen on Reddit like this forever. It's one of those things that now whenever I see a Chicago I see a robot.
I remember like we used to see it as like a priest with the Bible. Yeah.
You guys are killing it. Thanks for letting me sit in.
Bye.
Yeah, I'm like, wow, she's getting a lot of. Really good. And my first thing, like,
She liked it.
because I'm so used to you sitting there, I just, for the longest time, I'm like, that's not her. No, that's not. Is that her? That's not her. That
I
can't
felt
be
the
her.
same thing when I first came.
It's like, it can't be her.
Yeah, I thought like you had like dyed your hair.
Yeah, I'm like, she's got a shirt. Like, there has to be like multiple. What?
Well, now with the masks, like we can,
Yeah. Yeah, let's say it's the max. Yeah, yeah.
Okay, the title for my video is called Next Gen Virtual Human. So like the team is talking about if we having this like meeting virtually and then everyone has their own virtual avatars, how we can create those virtual human do exactly what we do and also like look really realistic. So for this presentation is little bit different from the others I already heard because like it's talking about the process to generating this stuff instead of just one single techniques. So the one they are talking about how to generate this kind of virtual humans in two aspects. One is motion, another one is how we generate the clothes for the virtual humans. For the motion part, the first because the ideally the most traditional way we want to track the motion of the people is we have the multi-view camera system, which is a green room we usually say. You ask people to in there and there are some multiple cameras and take shots on you, then the computer can try to infer what's your motion, what are you doing. So they are talking about just use a single point of view how to generate that. So they introduced like a dense rack system. In the before, there are already some technique can try to capture the motion just by one single view. I guess it's called open pose and NBF. They already have the techniques. But what's the difference is like the technique I just said, they use the single RGB image, then try to extract the joint data, and then reanimate the 3D models. What's the difference in their method is they instead of directly use the RGB input, they first generate a map called generate a visual map on the second, which is a really colorful one, by dense landmarks, which is the density of the surface of that part. So using that, they have a huge database they can compare to. So they will using this IUV input try to guess what's the motion of that single images. During this process, there are two important functions. The first one is render and compare, which is try to fill the missing part of the single RGB input. For example, in the picture on the left arc is kind of missing in that single view, so it's a missing part for the computers. So using the database, they will fix that part, and also like there is a joint learning, so they have a large data set from the real world about joints, like which part is reasonable if you join is over here. Using that compare with database, they will fix the joint in that RGB output. Then they can get then they can track your motions in a single view. And also, what's good for this one compared to others is they can track multiple peoples in the same scene, because when you have multiple peoples, maybe they will overlap each other. Then the old ways where maybe the joints will fly because they are not sure which is whose hand, maybe whose arms. But by using the dense marks, they're able to even map the different people in the same single views. And besides this one, they also talk about how we form the clothing, because they don't want to only produce people without clothes. So another technique they introduce is arch, which is using a single RGB input to get a 3D model close. So using the RGB input on the left. Using this technique, they will compare to a database which contains a large group of datasets with 3D scanning of people wearing clothes with different poses. So by analyzing that single input, they are able to map the colors and which part of the clothes into a 3D space, so they can generate the clothes and hairs for the characters. And to make that clothes make more realistic is like they introduce a text mesh, which help them to generate the deformation of the clothing when you are moving. So this technique still using a single view RGB, and when you tell the system the lighting in the scene, they will generate a better, I'm not sure how to see that, a better images, and compare with the data sets they have, like how, like if you move your shoulder, how the mesh wheel works, how the mesh wheel moves in that part, and they generate the texture reset, then they will get the output for that. And also, like if you have a high resolution code, and then you are trying to run the simulation for the physics, that's really time consuming. So they also introduce another technique called deep wrinkles, which is using a lower resolution of the clothes with less meshes, and they try to simulate the physics on the normal maps of the clothes, which saves a lot of time and makes the performance better. And the last thing they introduced in their process is size-free. This is a system with a huge data set, which have the people with different kind of clothes, because when you wear the clothes that suits you, that's have one kind of deformation. But if you have a clothes that's bigger than what you usually have, or you should have, the deformation will be different. So this system just have the data set with hundreds of models and data set for people with different size of clothes. So this is the whole process they're talking about.
They get so the idea is that they get from a photo.
Sure.
They can create a 3D human.
Yeah, and also like by using this one, you can just have a single camera to track all your motions and also like simulate everything on you.
Did they mention what the like per frame rendering is? If you do a video, like could is it real time or
I guess from what they are showing can be real time.
Oh really?
Yeah.
Okay. That's sweet. I had a question about the first technique, the first
The
slide that you mentioned.
yeah, the rack grab.
The one where the guy with the plate. Yeah.
Sure.
So on the left hand side it says mocap and 3D scans to get the skin render. Are they using, like, if they already have a 3D scan of a person, why do they have to go through the whole reconstruction process? I guess is my general question. Or is it possible to do this without a mocap and 3D scan of the person?
Oh, you don't have, like, this one is just like what they're talking about for this one, but for just tracking for emotion, you only need the RGB input
Gotcha.
for that.
Alright. So this is specifically to get the.
Yeah, this one done.
Okay.
Yeah.
So I think that here he's going to go to open pose to kind of like match like the database of existing poses.
Yeah. Like they have the database with video of poses from a single view, so like this one, there's one similar in their database in PBR.
So what do you think will be an application of this technique? What are they going to use for?
I would say a lot, because since seems like they can do in the real time, they can just have like the virtual communication they have. Maybe just like this meeting, they can do that virtually. Yeah.
Oh, so that you can have it.
Yeah, I can have my avatar look like you, dress like me, and we can just present.
And you could do VR, and instead of having like IR trackers.
Yeah, they have.
You could just have a single camera.
Yeah.
Yeah. Oh, could you give me the depth? No, it's just the RGB.
Yeah.
Yeah,
so
just
in theory,
one.
you could just do webcam input straight in.
Yeah, I guess. Can I show the video? I guess it's much more here. I'm not sure. Can we go to the video link so we can show some? Because I consider about like the number of slides we have, so I didn't put any.
So some interesting thing is that our next speaker is Tony Tom.
Like this is the database they have for that. How do you recognize that? And also like this is like the kind of output they
Anywhere
have.
in the scene.
This one is their
Our
result.
method is suitable for real-time system at 20 frames per second.
Could they see this from multiple viewpoints?
Yeah, I think so.
What I'm saying is like, could you then, like, is that actually a 3D shape that you could then, even though the camera's here, see what it looks like from this angle?
Just matching the observations.
They have an end result.
Given a style distribution that can be captured and driven by limited sensors. In addition to the visible layers, the non-visible layers also need to be properly modeled. Even though they are more permanent, even when we are physically remote from each other.
I guess they work on this one for many years because some of the techniques they mention is already published, I guess, 2 or 3 years ago, before this speech even. So like they continue work on that, so that's what they do.
Maybe you'll be ready for like COVID 25. Okay, thank you.
Is it also here?
It's in bright space, yeah. Alright, so the video I watched was called Perceiving 3D Human Interactions in the Wild, which basically just means in real life. And so what they were trying to do was kind of improve upon the present reality, which is most 3D human interaction capture happens either in this type of scenario with like complex depth multi-view cameras and markers or in front of a green screen, and they were trying to do more recognition from like real world scenes. So they focused on two things, two separate types of human interactions, and we'll talk about both. The first one was specifically focused on 3D human hands interacting with objects. So they said that the existing hand object data sets were all kind of based in the lab, and it's the same sort of thing, like in front of a green screen, very contrived. And so again, they were trying to see what can we do with like real world images, and I think they had some sort of bank of real world images that they were pulling from. And in this process, I'll try to explain it as best I can, but one thing that's important to note is that they took the philosophy of embracing CAD models. So they were not recognizing the objects automatically from the 2D image. that's like a super challenging problem. So they thought, okay, let's just use a CAD model. So the first step, you can see up there, there's kind of a flow chart and it maps to what's below. So A, the like bottom left rectangle, is the hand pose estimation. So from the image, they would like estimate the pose of the hand. Then next, and they had like hand model already because most people's hands are similar. So that one's a little bit easier. Then they have the image. I'm pretty sure, from my understanding, rewatching that part multiple times, a human would choose from a set of like 300 CAD models which CAD model best goes with the object. So in this case, maybe that's like a water bottle, even though maybe that's some cookie spray. I don't know what that really is. But then the part that was automated is it would automatically like select the best position of the CAD model that would match what was being shown in the image. Then they would do joint optimization. Basically, now you have the hand and you have the object. Here, your water bottle. Can I use it?
Yep, go for it.
So then there would be an algorithm that's gonna like automatically connect them as best as it can. Then the final step is pose refinement, and you can see there's like that hand that's kind of like this, and then they have an algorithm that makes it a little more natural, kind of wrapping around. So it's kind of a combination of some like human intervention portions and some automated portions. So this is another illustration of what they did, and here we see the same example that we already saw on the far right, but 3 other examples. A hand in a pen, a hand in a phone, a hand in a jug or something. So you can see first the same steps, the individual optimization of what's the angle of the object, what's the angle of the hand, the joint optimization, sticking them together better, and then the refinement of making it more natural. Okay, so then this is the second part of their project, which is completely different. This part, they were doing human mesh recovery from multiple shots, and in this case they said they were using movies. Obviously this is a television show, not a movie, but they were using movies and television shows. They said that part of the reason that they chose movies and television shows was it has long-range human behaviors, so kind of like humans doing something in a big sequence. They said that normally movies are challenging for computer vision because there's a lot of shot changes. Like it shows the person from one angle and then it shows the same scene from another angle, and usually the computer vision algorithms will be confused by that. And then another thing that's difficult is partial body views. So when part of the body is cut off, the like body recognition algorithms don't work very well. But they had some kind of strategies to actually capitalize on those and turn them into opportunities. So basically, they decided to treat the shot changes as a multi-view signal. So what that means is they kind of told their algorithm, like, hey, this is the same scene, just from a different angle. So again, there's some human intervention, but then they thought that could be beneficial overall. So if you look at this, basically what you're seeing on the far left of each, well, it's 2 examples. The left-hand column is the regular movies. The middle column is kind of what would normally have happened if they didn't use this multi-shot approach where they told the algorithm, hey, this is the same scene you just saw from a different angle. So when the algorithm tries to just recognize some of the poses without that information, it would be completely wrong. Like you can see in the bottom, there's like a butt instead of a face, or somebody's like flying through the air. So they thought this is actually an opportunity. We can understand how humans are behaving better if we just tell it that these are the same shots. They also thought that movies were like a rich data source, whereas other people had maybe previously said, oh, the scene changes make them bad, or the camera changes make them bad. They thought, actually, movies are a really good way to study the way that humans are interacting. So then my final comments. I thought it was cool that they were using movies as a data set because relating back to our conversation last week about just like privacy, it seems like if you're in a movie, you consented for people to view these images of you. So that's kind of more ethical than maybe using random videos online of people. One thing that I thought was weird, but that was definitely covered really well in the previous presentation, is in this case, they're just using like this man body for everyone. But I really liked the work that he showed where they were really trying to like get a sense of, oh, bodies come in all different shapes and sizes and have all different sorts of clothing and everything. 'Cause I just wonder, you know, does everyone use the same sort of poses depending on their body shape or size? Like probably not. But they were using this same creepy man for everything. Yes. Alright, that is it. Yes.
So you say for the first process that they did,
Mhm.
the like grabbing
Yeah.
pose animation, like the only manual part was selecting the tab model, right? And so I'm assuming that once they have like the tab model selected and they've done like one process, you could probably give them like another frame from a different like video or a different angle and have it reconstruct that, right? Or is it only
Probably
for
so.
this specific image?
I think if it knows, I would have to go back and look about the hand pose estimation if there was any manual part of them like sticking the hand in the right spot. I don't remember. I could see they did show that they were like masking the object and then use that mask to choose the right angle for the CAD model, and now I'm not sure again if there was human intervention to make sure that the mask is just covering the object, because you know it has to be, right? Like how does it know to mask the water bottle? It's not going to know that. So there are definitely multiple human interventions, and I don't think that it could have, I doubt that it could recognize a water bottle the same way that they could successfully recognize a person in the movie scene, because there's just been so much more recognition of people, and it's easier.
Interesting. Like, and if you like, what you said about like movies being like a good data source, like even like for creative, you know, projects too. But I feel like there's so many of them that you don't think about that as a data source.
Yeah.
Scientific, you know, for scientific research.
Right.
Really good.
And long shows like Friends had thousands of hours of the same sets with the same characters.
Yeah,
and
totally.
also slightly different positions, which is probably really, really good for some of the stuff like that.
Yeah, I could show the machine. Yeah. Cool. Well, yeah, thank you so much for such great presentations. I love like really
You know, seeing you getting to, you know, explaining like these hard topics in a very approachable way. So I really appreciate that, and also that now we all together get like a little bit of a better sense of what's going out, what's happening in the world of computer vision, like a very updated version, and actually like thinking again about all the things that we've been talking about in the whole class, which are, you know, like can we break down those steps of vision, and you know, I think like that they definitely have to do this process when they're creating these goals and so on. But like, you know, I'm not expecting you to do anything like this for final project. Like, don't worry about that. But like, I think that we want to kind of like approach this from the philosophical perspective. Like, can we break down the tasks of whatever you want to know about an image? Okay, so today I'm just going to end with a reminder that for next week we're going to have chapter 3 and 4 of Hoffman. But before we end the class, I wanted to get some feedback on how did you like this activity from today? You,
I like working with someone.
The videos were really complex though. I had to watch it like one or two or three times, kind of like understand what's happening, especially because I don't have a lot of education in AI and all that kind of like really technical stuff. So there's a lot to that.
Yeah.
I'd have Paul explain some of it to me.
You could watch mine. It was a
Okay. Yours looked pretty cool.
Yeah, so interesting. Well, thank you so much, and have a great weekend, everyone. I just got to say like thank you. It was like very enjoyable to see you present. So I like these Goodwill suits. Yeah, they're amazing.
They were my dad's.
Oh, really?
Yep, and he was gonna throw them away, and I'm like, I love them.
So the red tag is because
And
you
that's probably
wash
for
them.
actual. Yeah, that's probably from actual
Oh,
laundry laundry things. Yeah, answer Michelle. Yeah. Oh wait, this is from a laundry or a probably.